Okay, hello everyone. Thanks a lot for the organizers for inviting me to this wonderful conference. It's a great pleasure to be in this distinguished audience. So I'm going to start very quickly because I imagine some of the people maybe not exactly fans of finance. I'm just going to remind you what the evil stuff we do in asset pricing and finance. Okay, so in finance, we are concerned with the prediction problem of returns. Okay, so you have a bunch of securities, think about stocks, and we would like to predict what those stocks are going to do. And why do we care about it? Because then we can make money, right? I mean, so the previous speakers, right? Previous speakers, they mentioned, you know, this portfolio problems, right? So this is sort of the problem that we are concerned with. Okay, so we have this return vector Rn. The laser pointer is not working, right?
In the middle?
Yeah, I'm pressing.
No.
Ah, this is okay. Thank you so much. Yeah. Yeah, so we have this return vector, okay, and in theory, if you take a second order approximation to any utility, yes?
You explain why so when you do the Merton-Samuelson problem, the optimal portfolio share that comes out of that is the sort of equity premium multiplied by the risk aversion coefficient and divided by the variance.
Correct.
Why does finance use the Sharpe ratio, which is divided by the standard deviation?
Sharpe ratio because it's scale invariant. So if you multiply returns by constant, the mean and the standard deviation.
It's the wrong thing for portfolio choice, right? The right thing, I teach this every year and I always wonder, the theory says that you divide by the variance. And
well, that's the solution, the optimal portfolio is.
The optimal portfolio.
Yeah, correct. But the metric, the right metric to measure the quality is the Sharpe ratio. Now, why exactly that is the case would require a little bit of a calculation. So you can show.
So there's not an easy answer. All right.
Not in 2 minutes, no, maybe 20 minutes.
I thought that might be.
Okay. Yeah. So this is the standard, mean variance optimization problem that we would like to solve, right? This is now conditional. This is going to be very important. You see, I'm conditioning everything on the information available at time t. I'd like to find this optimal portfolio, and the solution is given by this. This is vector of expected returns and the covariance matrix and the risk aversion coefficient, and finance people sometimes call this the tangency portfolio, okay? And so here already you see there is a problem kind of practical applicability of this beautiful theoretical formula, which is that if n is large, which is a serious concern in practical applications where, let's say, in the US stock market, we could have thousands of stocks, so n could easily be on the order of thousands, but even hundreds actually becomes a big number. We have to estimate this and this. Okay, so this is a serious statistical problem and obstacle to the applicability of this. Okay. Okay. So another thing I can do is that instead of inverting the various covariance metrics, I can invert the metrics of second moments. Okay, just a small sort of modification. And this version of the Merton conditional efficient portfolio is going to be useful for me because I'm going to call it pi t tilde, because it's related to this thing which is called stochastic discount factor. Okay, so maybe those of you who still maybe remember some classes in asset pricing, you remember that in order to understand how asset prices are formed, they are usually under this arbitrage condition. There is this animal called stochastic discount factor. And if it exists, then all returns these excess returns will satisfy this identity. Okay, and so you can show basically that there is this beautiful link between this conditional efficient portfolio and the stochastic discount factor. So this sort of tells you that basically if you can find the conditionally efficient portfolio, you solve two problems. First, you become rich because you have a portfolio that works and makes money. And second, you can also price all the available securities. Okay, so that's sort of cool because yes, it's an academic problem that has real practical value. Yes.
So do the finance guys know that there's no such thing as a stochastic discount factor when you have heterogeneous agents? Do they know that?
No, I mean, if markets are integrated and there is no arbitrage, then...
No, if you have heterogeneous agents and a constant relative risk for the utility, there's not a stochastic discount factor.
There is, it just aggregates preferences of these heterogeneous agents in a very complicated and nonlinear way. Stochastic discount factor is just a consequence of arbitrage. If you want, we can talk about it. I teach this as well in my asset pricing class. Actually, I'm going to teach it in this neighbor building in 3 weeks. So.
I'm sorry, what?
Eva Cárceles and Tony Brook and Daniel Pontirani at Pittsburgh have several papers on the existence of stochastic discount factors in models with
but I myself have 5 papers on this topic, so but it's all right. So it has nothing to do. Forget equilibrium, whatever. If there's no arbitrage somehow, okay, so then M exists and it's positive. Okay, but let's not go into. So right now you have to believe me. So if there is a mean variance efficient portfolio, then you can define stochastic discount factor using this beautiful formula. Okay. And so once we got this, then the big question of practical, relevance becomes how do you actually estimate these 2 quantities, the conditional expectation and this conditional second moment? Okay, usually in theoretical, papers of which I have the scene of also being a co-author, many of those, right? We kind of ignore this. Okay, but in the practical real world, this is a serious concern. Okay. So now suppose that returns have a thing which is called a factor structure. Okay, so suppose that returns are driven by factors, and here I'm going to assume something very interesting. Okay, I'm going to assume that there are those factors that drive the whole structure of returns. Those factors are latent, means they are not observable, and the exposure of returns to factors depend on things that, as surprising people call characteristics. They are basically observable features of stocks. Okay, so every stock will have a price and return over the last year, and maybe its market to book ratio, etc. Those are called characteristics. And one of the common assumptions today in this asset pricing literature is that these betas to these factors, they depend on these characteristics. Okay, even if you have such a very simple structure, you can then show how to compute theoretically this conditionally efficient portfolio, and this is what it's going to look like. Okay, so the conditionally efficient portfolio is going to have conditional expectation, which will be linear in these characteristics, and this conditional covariance matrix, which is going to be a disaster because it's a nonlinear function of characteristics. Okay, so the reality is that if you dare or have the bravery to actually try to calculate this and with real data, you're going to fail. At least nobody has succeeded so far. We don't know how to compute conditional covariance matrices of stocks. It basically seems to be impossible. I used to work for a hedge fund. We had a team of 20 people trying to do this. The whole team was fired. So, so this is, yeah. So anyway, so it seems to be impossible, okay, because of various data issues. We just don't have enough data, okay? So the truth is that those objects exist, but they're not observable. It's a bit like string theory in physics, that there might be something there at super microscopic scales in the nature of space-time, but we will never be able to observe it, okay? Okay, so instead, what practitioners do is what now many people in asset pricing do, is they construct this thing called managed portfolios, okay? So you take these characteristics, ST, just multiply returns with those characteristics, and you build this object which is called factors, okay? And those factors are just basically sums stock return times the given characteristic, and you sum across stocks. You can build many factors of those, and some of you might have heard that there is this thing that today is known as factor zoo, okay, which is basically every year there's a paper that says, oh, I have found that this particular nonlinear transformation of available data predicts stock returns, and then you can construct a factor, okay? And so once you got those factors, you can construct the Markowitz portfolio of the factors. Now the difference here is that while here I was attempting to construct the conditionally efficient portfolio, so the portfolio that's efficient given the information I have at time t, here I'm doing something sort of simpler, where I'm trying to build the unconditional efficient portfolio of these factors, okay? And so here you can say, oh, unconditional portfolio is easy to construct because this is just an expectation, and this is just an expectation. And in economics and statistics and econometrics, we know how to compute unconditional expectations. You just take sample average. That's it, right? So that everybody knows. I used to teach MBAs, and then they actually know if you have an Excel spreadsheet, and I ask them how they compute expectations. They actually know you just take mean, right, of every column, and then that's a major discovery for them. Okay. So yeah. So now so the first thing is that it seems that here when you're doing this, you're doing some sort of reduced form attempt, because to build these factors, which is an inefficient object, you completely lose this information about this conditional covariance structure. And then you build this efficient portfolio of these factors, okay? And then, of course, you can build like a proxy for the stochastic discount factor just from the factors where the coefficients are constant, okay? So you can see that intuitively it seems that you sort of have lost some of the conditional information, in particular, this information and this unobservable and unconstructable conditional covariance of returns. And the first sort of striking result that we prove in this paper is that if the number of factors becomes large and we send the number of factors to infinity, the difference between the true but unobservable stochastic discount factor and the one that's observable, quasi-constructible from factors, goes to zero, okay? This is absolutely unique and depends crucially on this assumption that we call complexity, the fact that we construct a lot of those factors, like a really, really large number, okay? So that's the first thing that you will need to remember, that basically from now on, I'm going to work directly with this portfolio of factors. Now, what is this paper going to be about? So the main theoretical result is that, so what I just told you basically tells you that if you really want to approximate this true stochastic discount factor, the true conditional, Markowitz portfolio, you have to build many factors, okay? But when you try to build many factors, you're going to enter a different kind of statistical problem, because this vector is going to become high dimensional. And this vector will going to become high dimensional. Now, if you're an MBA student, you can still take the Excel spreadsheet. You'll just have many columns. And Excel now today allows for many, like thousands of columns. You can still do mean, right? and if you do this, you will still get an estimate of the expectation. And as an MBA student, you'll be super happy to have computed the expectation, okay? And some of the MBA students would even be able to answer why this is supposed to work. And this is the law of large numbers, right? The law of large numbers tells you that if you compute sample mean, you have sufficiently many observations, then you recover the truth, right? The true expectation. Now, the problem, however, here happens because this vector is high dimension. Let me give you an example. Suppose that I have 1,000 factors, and I have monthly data, and the typical example will be I have 60 years of data, so that will be like 600 observations monthly frequency. Okay, so I have 600 observations, my T is 600, and if I want to measure expectation of one random variable under normal circumstances, 600 observations will be enough to broadly get estimate its expectation, its mean. Suppose now, however, I have 10,000 of those variables. So each of them I'm going to get with a little bit of error. Let's say 1% error. Okay, so every expectation I'm going to get with 1% error. But I have 1,000 of those, so 10,000. So then to the back of the envelope calculation tells me that the total error of estimating the vector of means is going to be 10,000 times 1%. Right? Please forgive me for being not rigorous here, okay? So 10,000 times 1% is 100, right? So 100% error, okay? And that seems to be like a problem, because if I've estimated my vector of expectations with an error of 100%, then probably my estimation is junk, okay? Now, let's think about the same problem for the covariance matrix. So here as an MBA student, you will have a problem in Excel, but you might actually do it in Excel. It becomes not completely trivial. And once you've done that, you will realize that you've just estimated 10,000 times 10,000 covariance matrix. Again, for any given element of this covariance matrix, if you have 600 observations, you're going to get it. If everything is stationary, again, law of large numbers will tell you, you sort of got it right. But because you have 10,000 times 10,000, so it's many numbers, so it's 10,000 squared numbers, so divided by 2, it's symmetric, your errors will accumulate. And in total, you're going to get this matrix completely wrong. So you're going to get junk here, you're going to get junk here, and then you're going to divide one junk by another junk. Okay? And so then, people have kind of realized this a long time ago already, since the Markowitz times. And when people realize it, they say, okay, so what do we need to do? We need to find a low-dimensional representation. It's interesting, there were discussions of low-dimensional representation also today in some talks, right? So, and the thing would be, if I have a low-dimensional representation, you only have 3 factors here, then the law of large numbers kind of works. So I'm going to get 3 factors here, 3 by 3 matrix here, and I'm going to get some meaningful working thingy because of law of large numbers. But of course, I'm going to be very far from the true stochastic discount factor, okay? So you're facing this trade-off. If you try to build many factors, your estimation error is going to kill you, and the efficient portfolio you will build is going to be pure junk. But your model will have the potential to approximate the truth. By the theorem that you just saw, you build bigger models, you have the potential of approximating the true complicated nonlinear stochastic discount factor, okay? And if you take few factors, then your model cannot approximate the truth, but you get it right, okay? So here is the trade-off. And sort of the remarkable discovery we make is the first we prove it theoretically, second, empirically on the standard data set in asset pricing, we show that complexity works, okay? So we show that the performance of the stochastic discount factor is increasing in model complexity. What it means is that if I add more and more factors, my estimates become more and more junk, and yet they sort of start coming closer and closer to the truth, okay? And it turns out that this effect of coming closer to the truth always dominates, right? Always under some technical condition. And the striking thing in the data is that this technical condition does hold in the data. And that by itself is a remarkable empirical puzzle. Why is it that the nature of financial markets is such that this technical condition does hold in the real, US stock market? Okay. Okay, so now let me quickly explain what it is that we're doing. So basically, we are building a stochastic discount factor of this type. Okay, so we have these returns, we have those characteristics. I'm going to build a nonlinear function of those characteristics. Okay, and that's going to define this mean variance efficient portfolio. And the central solution that I already mentioned a few minutes ago is that it was, let's say, from a French key. Those of you who maybe remember, they sort of created this literature, the idea of factors, was many years ago. And they say, okay, let's just build a few factors. They introduce this value factor, size factor, there are a few others. And then you can build a stochastic discount factor, just a function of 3 factors. Okay, so this would be this example where the law-like numbers will work, but your model will not have the capacity to approximate the truth, so you will lose a lot. Okay. And okay, so now what is it? What is the sort of the machine learning meta problem here? Okay. So think about the universal approximation theory. Suppose we believe that the stochastic discount factor can be described by some complicated, unknown, nonlinear function of the data. That's a meaningful assumption, and for sure, for you guys who work on structural models, this is for sure always true in every single structural model that you ever write. All the models that we as economists write, they always have some Markovian structure. There's a state variable, and once you have the state variable, which could be very high dimensional, complicated, it's always the case that the stochastic discount factor and the prices will be functions of the state variable, and typically highly nonlinear. Okay? So once we got those nonlinear functions, the big question is, now suppose we believe it. Okay, so we believe it. The question is, how can you learn this nonlinear function in finite samples? Okay, and this question, how can you learn nonlinear function in finite samples, has been defining the progress of humanity for the last hundreds of years, and we'll probably define it further. Okay, this is a generic question. Think about the recent progress in machine learning and artificial intelligence. You all know ChatGPT. Okay. So basically, think about like this. What does ChatGPT tell us? It tells us that human language, the structure of human language, can be described by a complicated, smooth function. We will know what this function looks like. OpenAI secretly about it, but like, for example, Facebook published, a paper. We know what this function looks like. Okay. So suppose you believe that human language structure, whatever exactly it means, will take me an hour to explain, but so it's going to be very vague here. But imagine that the structure of human language is given by an unknown smooth function. Okay? You take all the language that we have produced so far as mankind, it's sort of an internet, right? And you take a large family of smooth functions that have the universal approximation property. Okay? Universal approximation property tells you that if I have sufficiently many observations, okay, and I train my family of functions on sufficiently many observations, they will converge to the truth. This is the universal approximation. Now, from my point of view as a practitioner who is constrained by the limited availability of data, the universal approximation theorem is absolutely, totally, entirely useless. Why is that? Because it tells me absolutely nothing about how quickly this function can be learned. Okay? There are certain classes of functions that cannot be learned from neural nets in finite samples. You can't, okay? So I can build you a smooth function that oscillates sufficiently, strongly, so that no matter how much data you give, trillions, quintillions of data points, it will not converge. I can give it 10 to the power, 300 data points, but we don't have computers that would be able to perform this calculation. So then the question becomes, can you build a function that can learn given the limited amount of data that we have? In the example of human language, it used to be believed that it was impossible. Okay, so many years ago, people thought the complexity, the linearity of the function that describes human language is so hard that nobody can build a neural net that can replicate it. And then they discovered a particular class of neural nets, a particular class of functions called transformers, whatever, that happen to be make these nonlinear functions learnable in finite samples. Now you could think, oh, those are big samples, like they have 1 trillion tokens, 10 trillion, but they're actually ridiculously small compared to the complexity of human language. Okay? So that is how the progress happens. So then, in my practical application, the question is there a class of nonlinear models that can learn how financial markets work in finite samples? Okay, this is the big meta question that I would like to answer. Probably won't be answered, but that's what I would like to devote to the next few decades of my life. And this meta question can also be considered in any situation, in particular macroeconomic structural models, right? I mean, we probably believe that there are those complicated nonlinear functions that describe the dynamics of the economy, human society, markets, etc. Question, can we come up with classes of functions, classes of learning algorithms? Because remember, just giving a class of functions is not enough. You also have to have a gradient descent algorithm and Adam and normalization and whatever. So can we come up with class of functions and learning algorithms that can learn sufficiently efficiently the truth in finite samples? Okay, that is the big meta question. So what does this paper do from the point of view of this meta question? What we say is that we take a super simple class of functions, extremely simple, the simplest possible. This is the class of functions that Kandin presented yesterday. One hidden layer neural nets, where the hidden layer weights are not trained. Okay, they are randomly generated. Only the weights in the output layer are trained. Why are we considering this particular class of functions? They are nonlinear. They have the universal approximation property, and I can understand them mathematically. This is the true reason, right? Now, what would happen if we train the hidden layer? What would happen if there are more than one layer? Nobody knows, okay? This is so complicated that, biggest mathematicians of, on Earth right now trying to do this, and they haven't got much progress so far. So, this is what's going to be about here. And so what I'm going to show you that for this particular class of functions, okay, for this really simple class of functions, if you want to better approximate the nonlinear nature of reality, you have to increase the number of parameters. Okay? So this is what we call the virtue of complexity. Now, is this a universal fact? Does it always hold? Does it hold for other classes of functions and other classes of learning algorithms? I have no idea. Unfortunately, nobody has any idea, right? I mean, so this can only be studied experimentally plus some sort of theoretical approximations. But one extremely interesting fact is the following. How have I convinced you that in this high-dimensional situation, the law of large numbers breaks down? Okay? Because law of large numbers breaks down, as you start learning in finite samples, you're going to learn something. Okay? So your neural net is going to tell you, this is the function that I have learned. And universal approximation theorem is going to cheat you, right? It's like a little demon sitting on your left shoulder, whispering in your ear, you found the truth. Universal approximation theorem tells you, this is the nonlinear function describing reality. But the truth is that is the demon and the angel sitting here, the angel is complexity, okay? And this angel is going to tell you, you're completely wrong. Whatever you found has probably nothing to do with reality. It's a tiny, inefficient, extremely bad approximation to reality. And is there a better way? I don't know, okay? Now, the cool thing is that you can use certain tools from mathematics, which is called Econometrics theory, and this is what we do here, to describe the gap. So this is kind of really fascinating. So the truth is not learnable. At least with this class of functions, we can rigorously prove that the truth is not learnable. If you want to come closer to the truth, you have to go to this infinite complexity. You have to build gigantic neural nets, okay? And they will give best results out of sample. And yet, they will capture only tiny piece of truth, okay? Now, while the truth is not observable, not learnable with this method, we don't know what it looks like, you can actually use this econometrics theory to estimate the gap between the truth and whatever you have learned. We did this experiment, and the gap is gigantic. I think we recover maybe 1% of truth or something like that. But that 1% of truth is already enough for us to, in the backtest, on the data, make significant amounts of money. Okay, in the simulation, unfortunately, not in real. If it was in real, I would not be staying here. I would be on my private island, you know. So, yeah. So, what exactly is happening, and what kind of truth do these models recover? And here it becomes extremely interesting, and it turns out that human beings knew this stuff way before this conference even started. And it turns out that the first guy who realized this was Plato. You know, a Greek dude. He lived like more than 2,000 years ago, and he introduced this idea of Plato's cave. Okay, so what is Plato's cave about? Maybe some of you don't remember, but he had this idea that human beings are basically prisoners of a cave. Okay, so when prisoners of a cave, kind of chained to the floor of the cave, and behind us stuff is happening. Okay, there's like light and stuff is moving, etc. But we can only look at the wall in front of us. And so what's happening is that the truth is there, and there's light, and the light projects the truth on the wall. And because we can't see the truth, the only thing we see is shadows. Okay? And because those shadows do not provide sufficient information about the actual nature of truth, well, we are doomed to only live observing the shadows. It turns out that Plato, and he was a remarkable genius, one of the biggest, in the history of mankind. He got it right. What is a shadow on the wall? Mathematical terms, shadow is a projection. So you have a complicated nonlinear three-dimensional line, right? And you project it on the wall using the mathematical operation of projection. It turns out that exactly this happens in this limited amount of data thing. What the model recovers in this limit of infinite complexity is the projection of truth on certain space of functions in the infinite dimensional Hilbert space, specific, whatever, reproducing kernel Hilbert space, if you want me to be more rigorous, okay? But this is exactly what happened. You could prove mathematically rigorously that you can't learn the truth, but what you learn is the projection of truth on this specific subspace. The beauty is that you can measure the dimension of this subspace, but not the subspace itself. The subspace itself is not observed. So it's as if you are sitting in this cave and you don't know on which wall the projection has happened, which is sort of a really nightmare from the Plato point of view, okay? But you can have some properties of this wall on which, okay? So from this wall Plato's cave point of view, the whole machine learning research, including large language models and whatever you think about, is about building new walls in this cave. Okay, we as humans, because of limited amount of data, we will never, ever be able to learn the truth. The nature of reality, including financial markets, macroeconomy, is so nonlinear, so complex, that it's simply not learnable in finite samples, at least as of today. Okay? However, we can build new models, new classes of neural nets, new algorithms for gradient descent, and each such model is a different wall in this Plato scale. So we'll be observing, oh, if I project this on this wall, it looks like this, it's a circle, and here it's an ellipse. What does it tell me about the actual shape of the body, right? I mean, so this is sort of how you can think about it. Okay. Now, conventional, as I said, yeah, so despite, and this is what I remember, so despite the inverse approximation property, whatever you learn is not approximately equal to the truth, because the law of large numbers breaks down. And this is the particular class of neural nets that I'm going to study. Again, the only reason I'm doing that is because they are analytically, well, let's say tracked, right? So to prove the stuff that we do here, it's about 120 pages of calculations, right? And that, you know, when they're doing more complicated nets, it's not about having more pages, but that's because nobody knows how to do those calculations. So, yeah. So this is the factor construction, as I said. So basically, we generate a bunch of nonlinear transformations, those are this hidden layer. We have these neurons. We take this input data, we generate a bunch of nonlinear transformations, then take linear combination of those transformations with an unknown vector lambda. And the lambda vector is going to be learned infinite samples, and this is what I'm doing. I'm really doing what an MBA student would do here, right? So I'm really, you know, been sort of infected by teaching MBAs, right? Yeah, so I take these factors. Remember, there's a very high dimensional vector. I computed sample mean, okay, and I computed sample covariance matrix. And here I'm doing a little bit, I do this penalization, thing is called the reach penalty. And then I compute this efficient portfolio. And an MBA student will think that, oh, of course, well, this is the expectation, this is the covariance matrix, so I got approximately, but you see, I took this approximation sign and I put a little stick on it, and this stick is a negation sign. Okay, so this is the thing. Okay, so now what you can do, however, yes, as I said, you know that what you got is completely different from the actual efficient portfolio. But what you can do, you can still characterize the out-of-sample behavior and study how it depends on the complexity of the model you build. Okay, so this is a simulation example that is showing what's happening as you increase complexity, the expected return increases, and the Sharpe ratio is monotonically increasing as you increase complexity. There is this, if you don't penalize enough, so you could put this small penalty, then just like in the presentation that Kanyin gave yesterday, you will see there will be this little bump, so performance will drop and then increase it. Again, this is the phenomenon of double descent you might have heard about in this world of neural nets. And so then what will happen is that you're gonna get the true out-of-sample performance, and the true here, the word true means the out-of-sample performance that you would have if you actually knew the true nature of this nonlinear function. But because remember, the true nature of this nonlinear function is not learnable in finite samples, so there will always be a gap between your out-of-sample performance and the beauty of this random matrix theory mathematics is that you can actually compute this stuff. You can analyze it, study its properties. Okay. So then we bring this data to empirics. It's relatively simple empirical exercise. Computation actually is a little bit non-trivial because you have to, you know, work with a large number of factors, but the computational complexities here are way below what you guys would consider serious, so I'm not gonna spend much time about it, but the empirical exercise, and this is the empirical evidence. Okay, so what you do here, we build this very, very large number of factors, and here we plot the out-of-sample Sharpe ratio of these factors, and if you increase the number of factors here, what you see is that the out-of-sample Sharpe ratio is monotonically increasing. One interesting speculative statement I will make here is, okay, so is the following. So look what's happening. We're using a rolling window of 360 months, okay? So capital T, number of observations is 360, okay? And so let's take C equal to 100, which is roughly where everything flattens out. So C equals to 100 corresponds to 36,000 factors, okay? So speculatively, I could say that what this is telling me is that in order to describe the conditional dynamics of the whole market, you know, stock market of the United States, you need 36,000 factors. Why is this a crazy statement? Well, because it's much larger than the actual number of stocks existing in the United States economy. Publicly traded stocks are maybe 5,000, the liquid ones are maybe 2,000. So why do we need 36,000 factors in order to describe this dynamics? So this has interesting kind of, like, I have a speculation to make about the macroeconomic origins of this. Okay? I believe that the macroeconomic system as a whole is complex. What does it mean when I say complex? It means that there are some sort of, I don't know, again, speculation from a movie, like a butterfly effect type of things, okay? It means that something that happens to one little company, I don't know, some sausage factory in Texas, okay, matters for the macroeconomy. Okay, let me give you an example again for pure speculation. I'm just doing one more now, okay, so, but I'm a finance student, so I know about. Imagine that there is a startup somewhere that has the potential to disrupt Tesla. Okay, so Tesla clearly is a gigantic company. It's clearly a macroeconomic commodity, right? And it's a macroeconomic entity. Whatever happens to Tesla and Elon Musk has implications for macroeconomy. So if there is somewhere out there a small startup that has the potential to disrupt Tesla and bring it out of the market, information about this is already there, and this is a risk factor, right? So this way you could push this higher and think that those state variables that capture the whole structure of all the thousands of firms in the United States, they contain information, very subtle cross-sectional information Well, what's going to happen in the economy? And that is probably why, in order to sort of summarize all this risk non-linear information, you need 36,000 risk factors. Okay, but this is speculation. I don't have any proof. One would have to write some sort of macro model, you know, when this mechanism actually is taking place and then illustrate it, which I haven't done, and I don't know whether I ever will do, but maybe somebody can. This is just an illustration what happens for different size groups. So this, for example, is for mega stocks, which is roughly the largest 500 stocks in the US economy. You observe exactly the same phenomenon, just the Sharpe ratio is not as crazy as it feels if you also trade smaller stocks. How much time do I have?
5 minutes.
5 minutes, perfect. So then when I'll have my 5 minutes, I will very quickly show you something about the theory that is underlying this, because the theory by itself is extremely beautiful. So what exactly is happening there? So here's what I'm going to do. Okay, so I'm going to introduce this quantity, which will have this the infeasible Sharpe ratio. Okay, so the infeasible Sharpe ratio as a function of this rich penalty is basically this Sharpe ratio of an economic agent who would know the truth. He knows the true expected return vector. He knows the true covariance matrix of returns. In reality, nobody does, right? And so this is a totally fictitious entity. And this guy, he would achieve this infeasible expected return on his portfolio if he used the rich penalty Z. Okay, so that's why it's a function of Z. And I can do the same for the infeasible second moment of his returns. Okay, and now, as I told you, the empirical one is different from this infeasible one, and the covariance matrix is different, everything's wrong. And so the question is, how different is it exactly? What defines the gap between this infeasible? I'm going to focus on expected return now, okay, because it's the simplest possible object here. What is the difference between the expected return that could be achieved by this crazy guy who knows the truth, like, I don't know, Xi Jinping, for example, and the guy who doesn't know the truth but uses only, you know, finite samples? Okay, and here is this remarkable phenomenon, which is called the implicit shrinkage or implicit regularization. So what exactly happens is the following. There is a quantity here that I call Z star, which is explicitly computable actually from the data, okay? And this quantity for this particular class of learning models only depends on the covariance matrix of features, okay? And it turns out that the Sharpe ratio, the expected return that the realistically achievable is directly connected to the infeasible Sharpe ratio, to the infeasible expected return. However, instead of this rich penalty Z here, this Z star of Z emerges. What exactly does it mean, and why is it called implicit regularization? Think about this, that adding this rich penalty, so you have this covariance matrix, as you probably know, covariance matrix is degenerate in the data. So if you try to invert it, you get into solution. So that's why you have Z to regularize it. This is explicit regularization. Now, the remarkable discovery here is that the feasible portfolio that you estimate in this big data retrieve behaves as if you know the truth, but instead of using the rich penalty Z, you use a larger rich penalty. And this larger rich penalty is outside of your control. There's nothing you can do about it. It's determined by the nature of the data. And this implicit regularization is the reason why big data works, is the reason why ChatGPT works, is the reason why Chinese government can now recognize one person in a crowd of 100,000 people, right? Is this Z star. Basically, big data models, huge dimensional models, they implicitly regularize the learning algorithm, okay? And so the beautiful thing here is that if I try to put Z to 0 here, okay, if I push Z to 0, I'm going to recover the true unregularized Markowitz portfolio. But it turns out that Z star does not converge to 0. It effectively defines an implicit threshold, a resolution threshold beyond which we cannot see. Almost like I mentioned, like string theory, right? So there are certain scales in the space-time beyond which we just can't see. We don't have technologies to look at the space-time at the fine structure. So here, this is Z star. It defines sort of the threshold. And so what happens basically is that the principal components of your data beyond which you cannot look, they basically get annihilated by this implicit shrinkage. It kills them, okay? And this is where the projection result is coming from. Beyond the threshold, everything is killed. All the information contained beyond the threshold is killed, and that's why what you learn is the projection. Okay? Well, this is it. I think it's I'm out of time. So thank you.
If there's time.
Yeah, go ahead.
Thank you. This is really fascinating and of course quite mind-boggling. In the older time series literature, there's something called information criteria. And you know that it's always about penalties on parameters. Is there a way how you can connect this to say the complete library information and the optimal information criteria literature?
So what I know for sure is that if you try to use a Akaike criteria, they're gonna explode and will tell you what exactly the link is here. I don't know. It's a great question actually. So to compute, I know that some people in ML have done these experiments, and for sure if you try to penalize, Akaike will tell you don't go to complex models. But the exact computation hasn't been done. It would be a nice actually exercise. Thank you.
Okay, thank you.